In this session, let's talk about decision trees. Okay, decision trees are examples of classification models that we can use to predict something that is categorical in nature. By definition, decision trees builds classification models of a form of a tree. It breaks down a data set into smaller and smaller subsets, while at the same time an associated decision tree is incrementally developed. The final tree is a tree that contains decision nodes and leaf nodes. A decision node outlook has two or more branches, like sunny, overcast, and rainy, and a leaf node represents a classification or a decision. Okay, so in this slide, we see that we have the first root node called outlook. If our outlook is overcast, then we go to a leaf node named play equals yes. So that will be our predictions. If outlook equals overcast, then play equals yes. On the other hand, if we move right, if outlook is not equal to overcast, we look to a different predictor variable, which is wind. If wind equals true, or if it's windy, then play equals no. Otherwise, if wind equals not equal to true, if it's not windy, then we look at the last variable called if it's raining. If it's raining, we play. Otherwise, if it's not raining, we do not play. So that's an example of a decision tree in which we start off with the root node from the top and we go down to each individual predictions. So how do we generate this decision tree? Through what we call the ID3 algorithm. The core algorithm for building decision trees is called the ID3 algorithm. It employs a top-down greedy search algorithm through the space of possible branches with no backtracking. Okay? It uses the concept of entropy and information gain to construct the tree itself. And it is built on a top-down structure from a parent node and involves partitioning the data into subsets that contain instances with similar values or homogeneous in nature. So, we have talked about entropy, which is the main purpose of the ID3 algorithm. So, what is entropy? Entropy measures the homogeneity of a node. It's given by that formula. Gini equals 1 minus the summation of the probability of j given t squared, where probability of j given t is the relative frequency of class j at node t. So let's go to the tax data set. Okay, so the scenario here is that we would identify which ones cheats on their taxes. So let's calculate for the entropy of the class tax cheat. So we know that in the data set we have 3 yes and 7 no. So 3 are tax cheaters while 7 are honest people. Okay? So in essence, if we calculate for the Gini index for this node, it's just equal to 1 minus the summation of p of j given t squared. So it's just equal to 1 minus 7 out of 10 squared minus 3 out of 10 squared, which is equal to 0.42. Now, if the sample is completely homogeneous, it means that all of the values are either yes or no, which is 10, 0. The Gini index is 0. If the sample is equally divided, it has entropy of 0.5. Now, another concept used for the ID3 algorithm to generate decision trees is called information gain. Information gain, or the Gini split, measures the reduction in Gini achieved because of the split. Gini gain is calculated for the Gini of the parent minus the weighted average Gini of all the children. It's given by that formula, where the parent node P is split into K partitions, where Ni is the number of records in partition I. Let's calculate for the Gini split of this data set. So on this slide, we have Gini index of 0.4. Recall that this is what we've calculated with a distribution of 3 and 7. 3 yes and 7 no. If we split using refund equals yes and refund equals no, we can calculate for the distribution of the Gini index for the children. Okay? If refund equals yes, there will be 0 yes and 3 no for the actual tax sheet. And on the other hand, if refund equals no, then we have 3 yes and 4 no. So now let's calculate for the Gini index of the children as follows. The child on the left has a Gini index of 0 because it is pure. 1 minus 3 out of 3 squared minus 0 out of 3 squared, and Gini is 0. On the other hand, the Gini index of the right child is 1 minus 3 out of 7 squared minus 4 out of 7 squared. It is 0.48. Now, the Gini of the child is a weighted average of the child. So, we have 3 on the left, 0 times 3 out of 10 plus 7 out of 10 times 48. So, in essence, your Gini of the child is 0.34. Now, if your parent is 0.42 and your child is 0.34, then you have what we call a Gini gain of 0.08, which is just the difference between the parent before splitting and 0.34, which is after splitting. Now, how about the computation for Gini for continuous attributes? For efficient computation of this attribute, we sometimes sort the attribute on values, and then we linearly scan the values, each time updating the count matrix and computing the Gini index. We choose the split position as the greatest Gini index, or the least Gini index for that matter. Okay, so in this example, we see that we would like to split the data through 97, the value of 97, because it gives us the 0.3 Gini index, which is the most pure split that we get if we are to sort through taxable income. So in essence, the split is less than 97 or greater than 97. So we have 3 yes and 3 no for less than or equal to 97, and if it's greater than 97, you have pure for no. Now, given all of those information, let's go back to the definition of the ID3 algorithm and let's construct a decision tree. Constructing a decision tree is all about finding the attribute that returns the highest information gain or the most homogeneous branch. Okay, we start off with the first step. We calculate the entropy of the parent class. So, we did that, and the Gini of the parent class is 0.42. Step 2 is we calculate the information gain for all the attributes. Since we have 3 attributes, we have refund, taxable income, and marital status. We calculate for the gains of each. And as we can see, we have tie gains for marital status and taxable income. Both have a 0.12 gain in information. So if there's a tie, we just choose randomly. So let's say we choose marital status. So now let's start building a decision tree by adding a node. Children node for marital status. So it's marital status equals married and marital status equals single or divorced. So if it's married, actual tax rate is 0 yes, 4 no. While if it's single or divorced, you have 3 yes and 3 no. Since the left node is pure, we can stop there and we can convert that into a leaf node since it is already pure. The leaf node will be again based on the majority class. So here, our majority class is no. So hence, if marital status equals married, cheat equals no. Now, we are left with the right node, which is single and divorced for marital status. And hence, we have 3 yes and 3 no. We can then do the ID3 algorithm again to further split the data on the remaining 6 rows of data. The 4 rows that were previously predicted are eliminated from the analysis. Okay, until all data is classified. So let's look at refund. If we look at refund, okay, the distribution would be yes and no refund. So if refund equals yes, we'll have 0 yes and 2 no in terms of tax sheet. And if refund equals no, we'll have 3 yes tax sheet and 1 no tax sheet. So now we have now a 2-level decision tree. As we know, the left child is pure, hence we can name that again as another leaf node. Okay, and then we run it recursively until we go through all predictor variables. And this is now your final decision tree from the ID3 algorithm. Now in this slide, we can see that from a decision tree, we can convert that decision tree into what we call classification rules, which are portable enough, and we can create business policies for these classification rules. Okay, from this setting, we've seen that if refund equals yes, then tax cheat equals no. So if refund is no, and marital status is equal divorce, and taxable income is less than 80K, then no. So as you can see, we move on through the different paths of the decision tree to come up with each specific rule. And we consider this most as mutually exclusive and exhaustive, and the rules set contain as much information as the decision tree. So basically, these are what we call rule-based classifiers. Okay, the rule-based classifiers are a version of the decision trees that are more portable, that we can use to come up with predictions. These are created using the Ripper algorithm. It is the same principle as decision trees. It is based on the frequency of each predictor variable. Some characteristics of the rule-based classifier. We have mutually exclusive rules. The classifier contains mutually exclusive rules if the rules are independent of each other. Every record is covered by at most one rule. And a rule-based classifier must also have exhaustive rules. The classifier has exhaustive coverage if it accounts for every possible combination of the attribute values. Like each record is covered by at least one rule. So in essence, if you have a mutually exclusive and exhaustive rules, then you have a good rule-based classifier. So how do these classifiers work, specifically the rule-based ones? Now let's say you have 5 rules, and you'd like to determine the class of each of these 3 animals. If it does not give birth, and if it can fly, then it's a bird. Rule 2, if it does not give birth and it lives in water, then it's a fish. Rule 3 says that if it gives birth and its blood type is warm, then it's a mammal. If it doesn't give birth and it doesn't fly, it's a reptile. And lastly, if it lives in water sometimes, then it's an amphibian. So if you look at the 3 rows of data, a lemur triggers rule 3, so it's classified as a mammal. So a lemur has give birth equals yes, and blood type is warm. So hence, it's a mammal. A turtle triggers rule 4 and rule 5. So in essence, it's not a mutually exclusive rule. Okay? So to do away with that, we use prioritized rules. So hence, if the turtle triggers rule 4 and rule 5, then hence, if rule 4 has higher priority, then we say the turtle is a reptile due to the priority of the rules. Now, a dogfish shark triggers none of the rules. Usually, a default rule is recommended. Hence, it is not an exhaustive rule. Okay, so again, this shows that it has a problem with mutual exclusiveness and exhaustiveness. Now, also let's define some performance metrics for rule-based classifiers. So the coverage of a rule is defined as the fraction of records that satisfy the antecedent of the rule. Okay, for example, if status equals single, then cheat equals no. So if we satisfy the antecedent, how many status equals single rows do we have? So based on the data on the tax data set, there are approximately 4 rows that have status equals single. Hence, the coverage of that rule is 40%. On the other hand, we talk about accuracy. Accuracy of the rule is the fraction of records that satisfy both the antecedent and the consequent of the rule. So out of 4 single status rows, how many have cheat equals no? So if you look at the data, there are 4 rows that have marital status equals single, and 2 of them have cheat equals no. Hence, accuracy is 50%. So, having said all of this, let's go through an example. So here we have a business scenario for the bank data. So a leading bank's marketing department would like to profile its clients to know which factors lead to the purchase of one of its flagship products called the PEP, or a personal equity plan. In this setup, 600 clients were gathered from the company's various databases, each having variables such as age, region, income, sex, married, children, car, savings account, current account, and mortgage. So in essence, out of the 600 clients, they were able to identify which of these 600 clients bought the PEP. And they would like to come up with rules such that when new clients would come in, they would be able to predict whether or not they will buy the new PEP product. Based on age, region, income, sex, married, children, whether they have a car, savings account, current account, and even mortgage account. Now, these are the lines again to use in R and R Studio using the RWECA library. So again, the first line is again to read the data, and we use the J48 command to predict PEP from all other predictor variables. We output the model using the plot J48 model, and we get this value. Yes, you can see this is a very useful decision tree. However, some people didn't like this because of it might be too bushy or very hard to read. That's why we also discussed the concept of JRIP, or the rule-based classifiers. It is similar as compared to decision trees, but it's far more efficient in predictions. Okay, so if you run these lines of code, you'll be able to run the JRIP model, or a rule-based model. So this is an example of the same data used on the back data set. Now, how do we read these rules? The first one is, if income is 29,000 or greater than 15,000, and children is greater than 1, and it's less than 2, you will buy the PEP 102 out of 109 times. So in essence, we were able to identify the profile of our clients that buy the PEP. Okay? So in essence, we can come up with campaigns to target these specific customers that buy our products. Instead of sending all of brochures to all of our customers, we will be able to target which customers are likely to purchase this new product that we have for sale. Okay, this again will provide us with better insights and better predictive analytics methodologies for our stakeholders. Okay, which brings us again to our advantages and disadvantages table. This time, talking about decision trees and rule-based classifiers. Right? In terms of complexity, it is not a very complex methodology. Okay, there are other algorithms that are more complex than decision trees, so it's an advantage. One good thing about the decision trees and rule-based classifiers is that it has no assumptions. We are not assuming anything. We're not doing anything. We're not assuming that the data are independent. We just feed the data into our model, and that's it. So that's sometimes an advantage. In terms of pre-processing, we do not do anything still. We don't process our data. We just plug it in the data and that's it. Hence, it is an advantage. However, when we talk about decision trees, it is an advantage if your data is purely categorical, and it will work poorly if your data is purely numeric. So hence, it is very powerful for categorical data, but very weak for numerical data. In terms of parameters, there are not much things to need to specify for decision trees, hence an advantage, as well as its speed. Decision trees and rule-based classifiers, if you run the source code previously, it's a fast algorithm. So we'll get your results instantaneously. In terms of handling outliers and noise, it's also a good methodology because we are just getting slices and dices of data. So outliers and noise are totally ignored in this setup, as well as missing data. You can still get missing data on what's remaining, and hence you can come up with decision tree rules if you have lots of missing data. One of the good things about decision trees and rule-based classifiers is its interpretability. People really like decision trees and rule-based classifiers because they are able to interpret what is the model that has been provided to us. As you can see in the previous slide, the bank data set, we were able to identify policies of which customers or which demographics of customers buy our PEP. However, in terms of relative predictive power, it's just in the middle ground. It's not one of the best terms in terms of predictive power, but it really goes into interpretability. Another weakness of the decision tree classifier, rule-based classifiers, is stability of the model. A little bit of change of the order of the attributes should have a different decision tree, which some people do not like. So it's basically an unstable model. Hence, it is a disadvantage. And lastly, the decision tree and a rule-based classifier is not optimal. We are not yet using any optimization models here to optimize our predictions. Hence, it is a suboptimal model. So in essence, in this module, we were able to discuss two types of classification models, specifically decision trees and rule-based classifiers. We applied these two methodologies on a bank scenario dataset in which we would like to identify patterns or policies to predict whether or not a customer would buy a certain product.